Morning, everyone. I was going to give you a talk for 90 minutes, but it seems to be 40 minutes. So I guess you guys have handout, but let's skip to first 10 pages. Okay. So I'm going to introduce mainly my work on autonomous driving. So I was working at Nagoya University until last March. And mainly I was working on autonomous driving. So I'm going to present what I did in Nagoya. And I'm still actually a part of Nagoya University. And I still work with the team. So originally, autonomous driving at this university, I had a little experience. So I had to start everything from scratch. Means that we didn't even have a car. So we bought a car, and we made a hack to the car so that the computers can control the vehicle through some interfaces. Of course, you can give some questions if you have any ideas. So it's going to be, I prefer interactive sessions, but if you don't have any questions, that's fine. So maybe this graduate school program requires you to have skills on analysis, data analysis, and data sensing, and control, and implementation, and so on. So this is pretty low-level engineering because we actually had to, make a modification to vehicular networks, and this is actually what we didn't actually work by ourselves. We asked the company to make such hacking to the vehicle because, this was 4 years ago, and I didn't see any work and activities that make cars available for, external computers. So you can see that we added a black highlighted components. They are not originally in the car, so we added black components in order to control the vehicle from the computer. Pretty easy. It's just some expertise is necessary. But once you add black box components, now you can remote control the vehicle. It's not autonomous. Be careful. It's not autonomous. You can just manipulate the steering and accelerate and brake from remote control because now the vehicle is connected to the computer. And what we did next is we put the computers in the car because remote control is boring. What we want to do is to enable the car to think how it should drive in real time. So this is not a vehicular grade computer. It's just a personal computer, but it was good for experimental systems. Generally, I believe that most researchers, developers, they first use computers such as a personal computer or laptop computers for prototyping. And then if the prototype is successful, it can turn into more production quality systems. But this is pretty experimental system. Not only computers, but also we need sensors because only computers, it can compute and calculate, but the car doesn't have any information from the outside of the vehicle. So it needs sensors to to detect what objects is, around the vehicle. So we had a couple of sensors You may know a camera, right? Because you often use camera with smartphone and so on. But there are a lot of other sensors, such as GPS, laser scanners, round view cameras, and so on. And some people also use milliwave radar. It's not laser scanner, it's a radar. But our prototype system didn't have a radar. And it's actually up to you, what sensors you want to use. So in our case, first we used only laser scanner. No other sensors are equipped, only laser scanner on top of the vehicle. And this is 3 months after we introduced the car. Only 3 months, because we made a team formation, including computer science experts and robotics experts. So we can, as a computer scientist, we are very good at implementing a system. On the other hand, robotics people pretty good at make the system autonomous. So we made first a collaboration, and only for 3 months after we made a formation, we made this demonstration. This is really elementary. It's like it's like a kid, because the car just follows the lane, and once some objects are showing up, it just stops, and once it disappears, it restarts. But this is real world, not simulation. It's a real car, real system in real time. Everything was made by ourselves actually. So this was good, pretty good. So like at this moment, we didn't have a large-scale team. We didn't have this program. We didn't have specific project at the university. So it was just a composed of my laboratory and a couple of other laboratories from other institutes. It's not official project. It's not official collaboration. It was just an experimental collaboration, but it did pretty well. So we decided to make this project more official, and Nagoya University actually started pretty large-scale national project on autonomous driving. I guess it was based on our outcome. They are my students, so some of them are my students, and they still working with me, in university collaboration or university company collaboration. So it was a good connection. So what we did next in order to proceed more, advanced technologies, because the demonstration that I just showed you only follows the lane and stops when objects appear. Then it restarts when objects disappear. And control is pretty, wide, rough. It's not, well tuned to make the steering, for example, move smoothly. One of the reasons why we didn't make the car drive smoothly is we lacked a high definition, information about geometry. So we next, looked into using 3D, high definition 3D mapping items, and some of you may be using such a 3D information in your program, but some may not. Anyway, this is interesting because once you run the vehicle on left top, this is measurement vehicle. Just running once in a city, you get a 3D information of where you drove. This is not real time. You have to take the data back to the lab or company and make some analysis in offline. But waiting for a week, then you get very high definition 3D information about where you drove. And I like this 3D, it's kind of modeling, because this is not computer graphics. This is based on real world data. And it is constructed by collection of points, 3D points, X, Y, Z. And there are more than billion points. Not as many, not as much resolution as image, because image is very high definition data. On the other hand, well, since this is 3D, construction and the collection of points, so the resolution is not as high as the image, but this is sufficient. Some of you may not believe this is not, 3D image. This is not image. This is a collection of points that the measurement vehicle collected. So for you, perhaps what is interesting to you is to extract information from such a 3D information, because human beings have eyes, so you can understand where is the lane, where is the zebra, where is the building. But for computers, it's not easy to get information from this low data. So what we did is to make more analysis to 3D data and extract more rich information about where is lane, where is building, where is traffic light, where is zebra, and so on. Then let's put this extracted information back to the original 3D data. Then you get more and more, rich information about geometry. So you know the shape of the place by 3D points, and you also know semantics. What, for example, the place means. Sometimes it may be buildings, sometimes it may be traffic light. And there is even virtual lanes, which was not originally on road, right? So we extracted such information from the 3D data so that autonomous vehicles can easily follow the center of the lane. And this was a good collaboration between university and the company, because university students don't have time to, make some hands-on on debugging or correcting or checking each information points, pieces of points. Instead, the companies are making a business, so they are totally fine with spending some time to, construct such a 3D rich information. And now, how we use 3D data. That 3D data has, I guess, multiple ways to be utilized. But one of our favorite is to use the 3D data for localization. Localization of driving vehicle means that the vehicle knows where they are driving. So in order to know or localize the vehicle, we use 3D data, and this is laser scanner, the data from laser scanner running in real time. So actually, the data format is pretty similar to 3D mapping data, because it's anyway eventually a collection of points. And there are lots of types of LiDAR in the world. And now, LiDAR means laser scanner. So I use different terms in same meaning. And this sensing is also interesting to me because I'm not an expert in this area. When I looked at the data, it looks amazing because it can easily scan the real-world data. It runs in real time. And we didn't write any lines of source code, just put some driver and install software for this LiDAR, and when we run the system, we get this data. So we always use such a laser scanner sensor for vehicle because it can precisely sense or measure the distance information. And for example, when you are driving, because laser scanner is equipped on top of the vehicle, it can always sense, what is around your ego vehicle. And the data is represented by collection of points. It looks like a circles, but it's a collection of points because it's digital data. Similarly, the 3D data of the real world that we constructed in advance is also represented by collection of points. So they are the same, similar formats, data formats. We can compare actually two different kinds of data because they both represent the shape of the world. If you are somewhere in this place, there should be one unique place where the shape of sensing information can completely match the 3D real world modeling data. And for example here, because we have two buildings, one, I don't know, looks like a wall, and one another wall here, and search for such a place in within this data set, and we find, if the vehicle is here, everything is matched. So we call it a scan matching, and this scan matching is performed every time sensor data is updated. So since the vehicle is driving, moving, the shape of the sensing data is also changing. And when every time the shape of the sensing data is changed, we repeat scan matching, so that we can trace the place of your vehicle. And here, this is not a log from driving data. This is the result of localization. We use 3D map data and this scan data by introducing scan matching in order to localize where this vehicle is located within this place. And the accuracy of localization is sufficiently high. It's a scale of centimeters. It's much more precise than maybe highly expensive GPS receivers. So since we can localize a vehicle by accuracy of centimeters order, that allows us to make an autonomous driving perform in a city, because in a city you need to know your precise place by centimeters order. Now we wanted to go for outside field testing, but one critical problem is that on the public road there are traffic lights. So we know where we are driving because the vehicle is localized, but we have to understand the status of the traffic light in order to follow the traffic rules, right? When traffic light is red, you have to stop. So in order to understand the state of traffic lights, we can also use 3D data, 3D map information, because you exactly know where you are. by accuracy of centimeters. And you also know where is the next traffic light because such information has already been extracted from 3D shape data before you drive. So you can reproject this 3D coordinate information onto, so image is 2D. This is data from camera, by the way. And this is kind of computation results from 3D laser scanner localization. We can transform the coordinates from 3D to 2D or 2D from 3D. If you successfully calibrate two different sensors, a camera and laser scanner. So a camera is actually on the front window and laser scanner is on top of the vehicle. If you calibrate these relative positions precisely, you know that when laser scanner finds something, then it should be corresponding to this place on the image. So we know that there must be traffic light because 3D information tells you there is a traffic light. There must be traffic light here. So we keep checking this space and try to recognize what is the color. So when the vehicle is approaching to the traffic light, now the resolution becomes high enough to understand the color information. So, by taking this approach, it is useful because, like this scenario, we know that there is no traffic light because 3D information tells you there is no traffic light. So you don't have to run traffic light recognition. So there is much less misdetection. Sometimes, if you don't have such 3D information or geometry information, you have to always check if there is a traffic light on the image. And there may be some misdetection because cameras sometimes doesn't work. But by introducing 3D information, geometry information, the precision of traffic light recognition can significantly improve. So that's what we got, this is what we learned from field testing. Now, because we know where the vehicle is, and we are also able to recognize the traffic light, and of course, we are allowed to do this field testing by police. So we have to negotiate with the local policies because sometimes we don't touch the steering. So sometimes police may believe that they, we are violating traffic rules because you are required to guarantee the safety of driving. So we need to negotiate with the police that yes, we don't touch the steering, but the computer is taking care of the control. So this is not violating traffic rules. And it's 40 to 50 miles per hour, fully controlled by computers because by using lidars, laser scanners, and 3D map information. We don't use GPS. We don't use milliwave radar. We only use 3D map information and laser scanner. Then made this demonstration. After it's also only 6 months from we started. So if you successfully made a formation of the team and you successfully choose the tools or devices or sensors, computers, you can also do this demonstration 6 months from now. And yes, Prime Minister has also come to our demonstration and they made some experience in driving. And we performed this demonstration by 5 students and myself. So it's not a large team. It's a university lab scale, right? Basically, you work with a few students. not often a team is composed of more than 10 students because 10 students are too much. So maybe 5 or 4 members would be, right size to make such a demonstration. And this demonstration was very successful because people know that we are working on autonomous driving. And the university also noticed that there is an autonomous driving team in Nagoya University. And almost at the same timing, Nagoya University started a large national project on, smart mobility. So since we are part of that large-scale project, and autonomous driving has become more, people started paying attention on autonomous driving. So we got a huge garage. Until then, we actually parked a car outside of the campus. So sometimes when it rains, we have to maintain a vehicle to be clean. But this is pretty nice to us because large garage allows us to, for example, set up parameters or tune up, vehicle state and so on. And we got more students. We started only a few students, but because we actually work on computer science and we also work on robotics, we also work on field testing, kind of real-world testing. So a lot of students among multiple divisions wanted to join the project. And I don't know how many members are now in Nagoya University who work on autonomous driving, but 2 years ago, this was 2 years ago, and we had more than 25 students involved in the project. If you are interested in autonomous driving project, you are definitely welcome to join the project. Depending on your expertise, I don't know where you come from, maybe engineering department, maybe information science department, whatever. You can use your expertise for automation or real-world testing. Yes, not only garage, but also we got a test course. So we didn't have to go for a public road every time because public road always there is some risk. So it was more preferred if we can use test course because it's, the environment is more safe than the public roads. And we had multiple autonomous vehicles for testing. Now we use 4 autonomous vehicles to test for example, connected activities like vehicle and vehicle are connected and exchange some information, not only for a standalone automation. So this encourages far more students to join the project because now, networking or connection, communication people can join the project. Some of the students may want to work on ITS, Intelligent Transportation Systems, because the autonomous vehicles are connected with each other. This is interesting environment for research and development projects. So my personal interest on this project was to develop integrated software that includes everything necessary for autonomous driving: sensing, localization, detection or recognition, planning, control. Everything is integrated in the software package. And in the same test course, this is a visualization of how the vehicle can understand the real world. So it's 3D map information is projected, and the vehicle understands where is the next zebra crosswalk, and it also knows what route it has to follow. In addition, yes, deep learning is one of maybe potential technologies to make something possible, which is currently impossible. And for image recognition, certainly we believe that deep learning performs very well. For car detection, pedestrian detection, by using deep learning, we are not expert in image processing, but using deep learning tools, we can reach here without involving any experts from image processing communities. Of course, if image processing experts join the project, it can further improve. But right now, we use existing deep learning tools to understand, to recognize objects on the image. So we are not experts in image recognition, but we are experts in computing. So for example, we like to use GPUs instead of CPUs in order to accelerate the computation. Do you know GPUs? This is somewhat a special device that can accelerate the computation of highly parallel applications. Image processing is one of highly parallel applications, so GPUs are suitable for accelerating such a workload. It is much faster than a CPU. Even for undergrad students, can speed up the execution of image processing by 10 times over the original implementation of CPU version of image processing. If the computation is 10 times faster, you can see this difference because the result of detection is the same. Yes, the pedestrian is detected successfully in both implementation, but because GPU version is faster than CPU, so it has a low latency. So it is more suitable for real-time usage. So I introduced two sensors for now. One is laser scanner. The other one is camera. And we use them together. We don't have to use them individually or exclusively. We can integrate two different sensors because they are both used for detecting or sensing the outside environment. For example, the camera gets this information. It's a 2D information using with RGB colors. On the same coordinate, we can extract how laser scanner senses the same angle, same direction of the view. So laser scanners are sensing the distance information. You can see red is close, blue is far. So it looks like a depth image. But you can use both information because, for example, data from the camera, image from the camera doesn't show you distance information. It's only a 2D. On the other hand, laser scanner information tells you the distance information, but not the color information. So we can integrate two different sensors. So what you can obtain from this sensor fusion is, you know there are cars, but you don't know the distance information if you only use cameras, because cameras don't know distance information. But you also have laser scanner information. So you know that the distance to the objects. And as I explained earlier, this laser scanner information and camera information are well calibrated. So they know their coordinates So when cameras detect object, cars, for example, laser scanner can tell you, yes, how far these detected cars are from yourself. If you have a capability of detecting objects, moving objects, including distance information, for example, you can do this, right? When a pedestrian is walking on a zebra, the autonomous car can detect by using both camera and laser scanner, and can stop. And once the pedestrian is disappeared, the car can restart. One more function would be desired to make the car more practical, which is obstacle avoidance. So far, yes, we can localize the self, we can detect objects, we can control the vehicle, but the car can stop. But at this moment, the car cannot still avoid the object. So to avoid objects, you have to generate a path which is not necessarily the same from the original route that the car was using. Say, basically the car is driving at the center line of the lane, but if there is a parking vehicle, you have to change the path of your driving plan. One of the way to achieve that is to use spline trajectory, which is since the car has a velocity and direction information, so you can calculate what trajectory the car can take under physical constraint. For example, a car is not Roomba, it cannot make a sharp turn. So you have to think about some physical constraint on trajectory generation. Okay, I can speed up. In order to select, so you have to select one of the trajectory for the next timeline of the vehicle plan, which can be, for example, determined by using LiDAR, laser scanner information. So laser scanner detects some obstacles. So you can select the path which doesn't crash the obstacles. One of, yes, the scenario that we like to use obstacle detection is to avoid a avoidance is to avoid a parking vehicle. Originally, you want to drive at the center line of the lane, but the car detects the parking vehicle here, so you have to change the path. It was selected from one of the trajectory that the car was generating. So the car is generating this set of trajectories in real time, always. And at some point, you have to select one if you want to change the current path. And yeah, I can conclude. So we published the whole pieces of source code that we developed. So if you go to the website, you can download our software, and it includes everything that I showed today. So you have to still buy a vehicle or a sensor or 3D mapping measurement vehicle, but once you have such set of hardware, you can implement by yourself, for example, localization or detection or trajectory generation or vehicle control. So everything is open. And this software has now close to 1,000 active recognitions. So about 1,000 developers in the world are now using the software. And we have kind of open source Slack community where you can exchange some information about the development of the software. And I believe there is no other open source software for autonomous driving. So people now want to use our software in order to develop a prototype of autonomous vehicle. Yeah, I can skip. So a couple of tips or extended modules. So we have large scale of map information, but the whole pieces of map cannot be installed in the car. So we download piece by piece. This is 300 meters square, only required for a local planning or detection or localization. When a vehicle is moving, it can operate from data center. Or you can also build the map by yourself, because the car also has laser scanner sensors. So if you use some function of our software, when a vehicle is driving, it can build the map by itself. So you don't have to now ask the third-party company to build the map. And our project is fun because we go to many places to do field testing. This is island in Aichi Prefecture. This is some city in also Aichi Prefecture. No regulation. We of course negotiate with the police, but there is no closed environment. This is pretty open. Other vehicles are not our staff. They are general customers or citizens. Yeah, we founded actually a startup company with professors and students using this research project. And we collaborate with Silicon Valley. We like parties, more field testing. More field testing. Yeah, this is interesting because it includes lane change scenario, automatic planning of lane change, because the car has to make a right turn in the next intersection. So car decided to make a lane change by itself. Yes, more at field testing. And this is the car we use. And potential users are take a ride on our experimental vehicle, because we want to get a feedback from such a potential users, asking if autonomous vehicle is deployed in a city, do you want to use it? Something like that. Or kids. And we called for many engineers, because we want to teach our software, how to use our software. Sometimes we go for mountain using the same software, but a different vehicle. This is in close to Fujisan, Mount Fuji. Because the car is autonomous, you don't have to look at outside. You can get into virtual world. When a traffic light is red, what do you want to do? Do you want to keep looking at the traffic light? No, maybe. You want to maybe playing some games. But because the car is stopped, you want to also stop on a virtual world in order to feel the same motion. Maybe you want to play shooting game in a virtual world. So if there are multiple users who use our software together and they are connected, you can shoot other vehicles in a virtual world. Don't shoot in a physical world, you will be arrested. Of course, virtual world You can do whatever you want. You can put some monsters in the virtual world. You can put some monsters in the virtual world. So this is all collaboration of cyber world and physical world, real world. And we build a car, install our software. So I explained only software side today, but we also build a car by ourselves because now electric vehicles are getting more and more cheap. So we can collect some team which build up the real electrical vehicle. Then we install our software onto this vehicle and complete an autonomous vehicle. Completely self-contained. Everything is built from scratch. Okay, this is it. So mainly I talked about autonomous driving, mostly a software side, but we also work on the hardware side. So if you are interested in a project, because Nagoya University has multiple units of autonomous driving, maybe your expertise to be useful to improve the project of Nagoya University. So if you are interested in that, contact me. You can join us for fun. Okay, thanks.